Welcome back to the final session of the Open Hardware MiniConf. So our presenter for this session is Bob Powers, who has been behind the scenes at many previous Open Hardware MiniConfs and has had a hand in the hardware design of quite a few of our projects and has done all of the heavy lifting this year on the Rockling board. So he's going to be talking about the Rockling hardware. And I was told to introduce him as some guy who does stuff. So here we have Bob Powers, some guy who does stuff.
Thank you. That's one of the things I do. That was intentional. Gentlemen, welcome to the shop. No, I'm not that guy. I always wanted to be a YouTube star though. John, thank you for setting this all up. It's a pretty good setup he's got here. So yeah, what are we doing here? We're going to talk a little bit about the hardware. I know Andy's covered certain sections about some of the signals and things that go on with the FPGA, but when I help out with these things, I generally like to talk a little bit about hardware design, the choices that get made. Usually some of the things we messed up. Again, John stole some of my thunder there, but most of those were his screw-ups. I've got my own. Don't worry, we kept a few in the bank. And yeah, that's probably about what's going to go a little bit into some ideas about if you're getting into hardware at like a hobbyist level, some of the ideas you might want to take on board and some interesting things that help out there. So first off, you'll probably notice a theme, and I should start off by saying these guys wanted to do a little bit of a end of day thing at the end. So they've chopped, just straight up stolen about 5 to 10 minutes from me at the end. But that's okay, because that fits in nicely with our theme. So I'll thank them for doing that. That was really apropos. Where's my focus is off. How do we get up there? That guy. That guy.
Yeah, focus.
Focus. I'm not that guy. Hello, everyone. So, welcome back to the good stuff. I'm not that guy either. Did anybody get that one? No? No chess fans? That's Agad Mator. He's the other YouTube guy. Those are the only two YouTube guys I know. First, we'll start off by thanking everyone so that I don't forget to do that. And again, back to the theme, it fits in, you'll find out how. The OHMC team, of course, I can't stop not mentioning them. Yeah, you've heard their names 1,000 times. I don't have the speaker notes up here, but it's basically everyone in this room. Andrew Nielsen, Steph Piper, who else did we have contributions? Andy Kitchener, yeah. You've heard their names a bit. Yeah, anyway, John Spencer, Lachlan stepped in a little bit. Yeah, everyone that said anything, there's too many to count, you know them. Then specifically the hardware ones I want to mention, there will be some thanks at the end too, but the guys at Gaudy Labs, they're the ones that we basically lifted the theremin front end from. FOMU and Icebreaker, they're the FPGA stuff so that we didn't have to think about that very much. And Paul Stoffegren, PJRC, you know, the guys at Teensy. Well, the guy at Teensy, I guess. I don't know. There's more of them. Yeah, you'll see why I really want to say thank you to them, but of course there are lots of others too. So moving on. This is me a little bit. I do professional consulting work in the area of electronics design. I do that so I can do this. I'm not going to plug myself any further than that, but I am taking work, so if anybody has too much money and wants to get rid of it, that's what I specialize in. So give me a call or an email. Either one will work. Just in case these are what we're talking about here, I'm gonna mostly skip over the party button. I don't even think I have any slides on that. That's been talked about a bit. I think that's been covered. And I really didn't help out, so I shouldn't talk too much about it. But thanks, Steph. You did a great job. It looked great. And it's, yeah, pretty good result. So cool. So the other two, we got the swag badge, which you guys have seen this. We've kind of waved it around a bit today. It goes that way. It's really not complicated. That's not a knock at Andrew, who did most of the work on this. He's very early in his electronics design career, but you can see all the wonderful work that he's done design-wise. And this is kind of encouraging because as powerful as this is the entire schematic you can see there. It's basically a couple of connectors, a dev board, a reset button, and a screen. So the idea that you can throw those things together you know, without knowing too much about anything, that's really powerful. But we've all seen that before. That's been the theme of OHMCs for 10 or 12 years now. Pardon me. So that's cool on its own. You can see that we even took half of the schematic just to kind of pass notes to each other and yeah, that's cool. So there are some things though, even as simple as it is, that and as cool as the design is, that maybe you can't see without kind of X-ray vision because it gets hidden by the overlay or the silk screen. The touch sliders are kind of much improved. I don't know if we've got any quantifiable data on that, but they're worth looking at. That's a really good one if you're getting into KiCAD in particular. The pad layout and the design of that, figuring out how that gets made and where the keepouts and things like that are. There's a lot that goes into that. So just opening that library component and having a look at it, that's kind of instructive. So I just wanted to point that out, and you can see a side-by-side comparison. This is really a cool thing, and it's really more artsy than anything that I would have ever made. So Andrew is done. He's a bang-up job there. So that's mostly what I wanted to talk about for that. So moving on to the other thing, which is mostly the thing I want to talk about because that's the thing I worked on, is this Rockling board. It's fish. I have it on good authority that John Oxer won about over 9,000 internet points for that photo alone, because it is just brilliant. How that even came to be is awesome. I wouldn't have put them in an ultrasonic cleaner because they have a little MEMS microphone on them, but that's just me being, an old angry man with a beard. You've kind of seen this idea as well. Andy's shown this to you. So why am I showing it to you again? Well, this is even more simplified, and really I want to point out for the budding hardware designer, if you were going to get into this, trying to take a hierarchical systems view is really the right way to approach something that gets a little more complex than just, a single schematic sheet and a fairly simple layout with two layers. So once you get into this idea that you can have multiple functional units, you really kind of want to separate them. It makes sense when you see it, but you kind of want to see it done. So I'm trying to lay that out so that you can get an idea here that there's only a few blocks, and once you kind of correspond this simple diagram to something in the schematic and then ultimately how that ends up on the PCB, that's sort of where I'm going to in the next couple of minutes. So the parts you see there, Andy's kind of talked about them. He even showed in much more detail the signals and the way that those get passed and what the protocols are and so forth. So I don't think I'll belabor this too much. You can look it over, and I'll return to this a few times as well. But focusing on the blue blocks in the middle probably gets you most of the way. So when you see that translated to a schematic, this is kind of what it looks like. And so this is the top sheet of the schematic. And going back to what I said about wanting to take a hierarchical view of things, this is probably the easiest and most natural way to do it. And KiCAD supports this well. Most of your CAD programs out there for electronic CAD or PCB layout, they're going to support this similar sort of idea. So these are hierarchical schematic sheets. We'll dive into each of those 4 blue blocks, and you can see that most everything else is just interface. It's either connectors or options, maybe some LEDs or something like that. But they don't do a whole lot. They're just how you access what's in the more functional parts in those blue blocks where all the complexity lies. So I'll quickly run you through those. It's probably pretty boring to the non-electrical engineer or those who aren't so inclined, but there are a few little things to talk about in each one, and I might have 1 or 2 things to talk about. So for example, we've got the analog front end. So this is where we're going to do some translation of a physical movement in space that's going to come up with a signal that our FPGA can then read and mean something from it. So what goes on in there? Well, first off, how we got there and our design philosophy was, let's not redesign this, let's just steal it. So we did exactly that. I opened up the Gaudi Labs KiCAD files, also in KiCAD. Well done, fellas. Thanks for that. And we basically just chopped theirs off right at the point where it went into the digital processing part of their circuitry. So this front end, this design, I didn't do this. I don't get to take credit for it. And this is the beauty of open source and the theme that I'm going to keep returning to about how wonderful it is to just involve yourself in straight up thievery. So did anybody show Andy K's simulation?
No.
Oh, I've got a link to that here. Yeah, I don't know if I want to jump out of the presentation later. We'll try and return to that.
It's a Falstead, isn't it?
Yeah, it's on Falstead. Again, a beautiful thing that's just out in the world. We'll do that, but that gives you a really good idea of how this works. Yeah, we'll find 2 minutes at the end to show you that. So what you see there is, it's pretty simple though. You have your antennas on the left, highlighted in kind of pink. And you see the hierarchical sheet on the left, the schematic symbol for it. It just shows you how it's all condensed into inputs and outputs from a block. This is a sort of, you know, seminal engineering thing. It's like things come in, things go out, and you get to ignore the rest of it, or at least you have to look in further. And so that's the whole idea I'm talking about. And so the outputs to the FPGA come out the other end of this analog front end. And there's some tuning that goes on with a DAC, which is a digital to analog converter. So that just, you put in a number, you say like 17, it puts out a voltage, say like 6.63 volts. And as you change the voltage, it'll change the tuning frequency of these antennas. That's really clear from the simulation. So, yeah, the only other thing I wanted to point out here is I stuck in a little experiment that I still haven't got time to do, which is whether or not I can cut out that DAC entirely and get the FPGA to do some direct digital synthesis. It's basically a fancy way of saying PWM, which is a fancy way of saying just flipping a switch on and off really fast, and getting it to do that tuning function in the same way that the DAC would, but only by using the FPGA. So that's kind of one of those cool things about FPGAs is they might give you the ability to get rid of other bits of hardware, which we've talked about, you know, once or twice today. So moving over to the FPGA, this is where the signal processing happens. There's been a lot of talk about this as well. The tools there are very cool. What goes on in there? Just everything gets connected, and the most important point about all of this is completely stolen as well. So how do you build a complex system, you know, maybe on your first or second try? Make somebody else do all the hard work and then steal the results. So the guys, Tim Ansel and FOMU project, thank you Zobs, you know, we basically just took all of your hard work here, and it's ours now. We get to appreciate it and make little fancy fishes. Oh, I'm gonna run out of time. You can skip most of this. This is just connectivity. There's a system clock. John's gonna talk about that later. It's hilarious. But really, this is better summed up just by looking at, you know, everything gets done in spreadsheets. This means where everything went on the whole PCB. Moving on. After that, you want to get some output. We've got an audio block. This has got an audio codec and an amplifier, which might be kind of optional in the end because the audio codec does output to a set of headphone speakers. That's the pink guy on there. I should be waving more props around here. One of the advantages of being a hardware guy is you get all the props. So this guy is great because we just got to steal this from Paul Stoffegren. So yet another block, major functional block, 3 out of 4 basically stolen. There is an amplifier that I took straight off of like some data sheet, and it basically works. So that's kind of a way of stealing as well. But another major functional block that was just, you know, easy to do, drop that in. Paul and the PJRC have already done all the work. Thanks, guys. And that even makes it easy for testing. So this was a pretty cool thing where, you know, Paul's got this dev board and a Teensy, and they go together, and the signals are right there. So in order to test it, you grab a Teensy, you grab the audio dev board from PJRC store, and you hook it up and you go, oh, that makes noise. And then you hook it up to your signal, or your board there for testing in the same way. And ta-da, all of a sudden you don't even have to populate the rest of the circuitry. As you can see, half of that board isn't even populated. And away you go. You find out that your audio codec works, and ultimately also that the audio amplifier works on the back end. So there's half the board functionality tested without even having to do anything. That was pretty cool. Then there's the power block. I'll mention this really quick because there's only sort of one thing that I also stole here. This is ugly, so I must have designed it. But there is power sequencing for the FPGA. This is a little bit different for most of your microcontroller projects. Basically, you're normally with an FPGA going to have several power rails. In this case, we have 3. That's not a large number at all. I've worked on projects with 6 8, 10 sometimes, I think. So, but they have to come up in a certain way. That's what a lot of this is doing, is just making sure that happens in the right order. And yeah, you can look at that if you want. Also, there's a sign about backfeeding the SEO to the swag badge header. Don't do that unless you know what's going on. Just don't. So that's, yeah. Right, so we go back to this guy. I don't even know why I did that. That's bringing it back together. So how does this all come together in a PCB? Well, you get Andrew to design you up a fantastic shape, which I know we've just raved about a trillion times, and then you try and smush it all in there. But you can see how the functional blocks all end up in the right spaces. So because they all flowed through kind of in that left to right way, you can see how the arrows kind of all go left to right, a little bit of back and forth in the middle, but mostly left to right. We can kind of see how the functional blocks end up being laid out on the circuit in particular areas. And so we have our analog front end, and the antenna connectors come in over on this side. And then we have our FPGA and support circuitry kind of lands in the middle. And then we've got our audio sections at the back with the codec and the amplifier. And it all kind of makes sense. You just put the audio connectors out by the back in the audio sections. You put the FPGA in the middle, and you put the power pretty much everywhere else, because that's got to go everywhere. So these are the design principles that real professionals follow. But it does make sense, and you get a really good result. So one of the cool things I wanted to mention about having a guy like Andrew design something for you is when I imported that DFX, he had these lines that were set out as guides, and you can see them up there. This is super handy because I put these on a layer in KiCAD, and I was able to use them as guidelines. And so it's very simple to just say, oh no, all the ICs go along the center line. The connectors go at this point here, and this is a 45-degree angle there. In fact, you can see how it all just falls together once you have those constraints. It's kind of interesting that kind of constraints always make the engineering, and this is a good idea. Oh, and another idea, wow, things went wrong. Another cool thing about working with these open source tools is there's great stuff out there that I didn't even know about this. There's this interactive bomb tool. I just want to give that as an aside. Super handy for prototyping. You just hit export and it generates this HTML sheet for you, and you can like mouse over groupings of your components, and it just shows you where they are on the board. So when I'm building up one of these guys by hand, because we're trying to do it quickly and cheaply, yeah, where do I put those 24 1 microfarad capacitors? Well, they go there. And that's a lot quicker than having open the design file and having to look around, do Control Fs and things like that, just to figure out why I've been able to find 19 of the placements, but there's another 5 left over. Yeah, so that's a great tool. Check that one out independently. I'm so out of time here. The antennas, they go there. You're going to want antennas when you get this thing. Also, there's a ground connection. That's the little, oh, where's this camera? It's over here. See how it's nibbling a thing? That's the ground connection. You need to run that off to earth ground if you can. If you've got a power supply that connects you to earth ground, that's the way I do it, and it works. I won't tell you why you have to do that. Just try it. So we had to kind of knock together some antenna examples, and these were some ideas I came up with, and you might want to try following some of them. Again, I get to have props. This was a cool one where it's just I grabbed some copper piping, and again, these can just be done with alligator clips running off to leads, and you run this into some 1-inch like conduit fitting. I knocked this together for $0 in about 20 minutes. The only trouble I had was that the 1-inch copper pipe doesn't quite fit in the 1-inch conduit fittings. There's meant to be a little bit of give in there, and the copper pipe doesn't have it. So, I had to do a little bit of drilling. That was awesome. That didn't work very well, but maybe if you just tuned it, and in this case it's really cool because tuning is done with an angle grinder. Yeah, give that a try. So that could be a cool idea. Maybe a better idea though is this one where we wrapped a bunch of old coax around some like 90 mil or 100 mil PVC pipe. And this is great because I just found about 20 meters of old coax sitting under my house, chopped it up. And there's one really cool thing about PVC, which you can drill into it super easy. So just like 8 mil drill bit, you make some holes, you run it in there. You've even got like cable retention. That's not coming off. This is also a really neat idea because the way the theremin sensing works, you could almost use it like a depth sensor. You could stick your hand in there. And then the third idea, maybe 2.5, would be you just get some magnet wire and do the same thing. So if you happen to have 100 meters of magnet wire sitting around, cool. So those were some ideas for antennas. And yeah, again, you can just alligator clip these on. The signal integrity is not going to be great on this. In our testing, it's not super great. But it does work. So I don't have time to give you numbers or anything on that. But ask questions later and experiment, because this is one of the funner parts of this whole thing. So this even worked as an antenna, just by the way, it's a 25-meter reel of extension lead. Yeah, it worked better than anything else. Okay, the other cool thing, this is sort of the third part that I'll just cover super quickly, is that I also discovered there's an IDE for these FPGA tools. That's how quick the open source world moves. And this is a graphical schematic capture type of IDE. So this is, you know, it's pretty cool from a hardware perspective, because I showed you earlier how much, you know, it all centers on the schematic, getting that information laid out in the right way and having your hierarchical ideas about the world, and that's how you build complex systems. Well, this makes it very natural from that same perspective, because you can just hook together blocks that do certain functional things, and that's more the way that hardware and FPGAs are going to work. So this is a very young project, but it's very cool. I want to bring it to everyone's attention because I hope people will contribute. It's written in Node, which I guess has something to do with graph theory. And one of the really cool things is that even I was able to modify this environment because it's open source. I had to change a couple of files around, and some of our stuff is similar to, you know, Tim Ansell's stuff. And so I changed a couple of files, and I can put Rockling into this development environment, and then it just kind of works. It took me about a day to figure it out how it works. So somebody who knows what they're doing, it'll be like 30 minutes. And it does work. Autoplay? No. So this was one of the greatest moments of my entire life.
Upload.
Linky. So if anybody's ever done FPGA development at all, you would realize that that's just completely magical. That shouldn't work. It shouldn't work that fast, and it certainly shouldn't be that easy. That some guy like me could be able to get all the software tooling to work and just go. So there we go. So why I'm super excited about that while I'm running out of time is this seems a lot like the Arduino environment. I won't be the first person to make these sorts of comparisons about the open source tool chains and FPGAs in this time in particular, but these things seem very similar to, you know, 15 years ago when you were just going, oh, well, I've got this Atmel design and I can put it into the Arduino environment by changing the pins.h file, and, you know, then it just kind of works, and then there's some libraries and I don't have to think about so much, and it becomes sort of easy and accessible, and all of a sudden what used to be a 2 or 3 person job becomes a 1-person job, and all of a sudden what used to take engineering skills can start to be done by, like, you know, artists and other people who are just sort of persistent. I thought that was awesome. So I just banged up this bit of code, and I think it's pretty much the same thing. And what's really, really cool is this seems even easier. And to say that in some world blinking an LED with an FPGA should be easier than blinking an LED with a microcontroller, that's a bit strange, but maybe we live in strange times. So iStudio, if there's one takeaway from this, please developers, look at that one, contribute time if you can, because I want to see that go somewhere. It's already cool. It's already, awesome. It is missing some things. But, you know, those are the obvious things to fill in, and I think that a lot of those can be done. So, you know, FPGA libraries and IP blocks, clearly those are always needed for everything involving FPGAs. Some kind of serial monitor, easy two-way communication, that's like straight out of the Arduino environment. A lot of documentation, and, you know, trying to figure out, the tooling and the things around it, library board management, blah, blah, blah. There's lots of work to be done there, but it could be super duper cool. And I hope that somebody who's better at coding and that side of things takes a look at it. So that's my call to arms, because no great TED Talk doesn't end with a call to arms. So hello, arms, are you there? Sorry, I had to do one. But yeah, so I think we got a pretty decent result. I hope you get this hardware soon. We used some of these things, and there's a bunch of other tools, but please help with those projects if you can, because they are super good. I have had a look at KiCAD 6, which is just out. Anybody that's looking at getting into electronics design so that you can make, something like that pretty easily. KiCAD 6 looks really nice. They've added a lot of really cool stuff. I'll just say that. It's definitely coming along, and it's definitely come along a long ways in the last 7 or 8 years that I've been using it. So yeah, and I think I'll probably stop there because these guys want to close, and I shouldn't have spoken so much. I missed a lot of that, but yeah. Oh yeah, John.
Oh,
yeah, so
you need to embarrass me a little bit.
Oh yeah, I will embarrass John. Oh yeah, I will just say the only thing on that list that isn't like free open source software is Snap EDA. I used a couple of their things, so but they seem like a really cool company, and I like them a lot. So do check them out if you're unfamiliar with Snap EDA and in any way involved in electronics design, because I find them useful, even if they are a company. So yeah, John wants to talk to you a little bit about what he said earlier, and
Yes.
he cast some aspersions my way. So I'd just like to.
If there is an ongoing competition for who has made the most mistakes in this project, I am so far in front that no one else can catch me, and we just discovered another one today. So my contribution so far has been talking about failures and mistakes and fixing them, and the issue with testing and the oscillators, which I kept referring to as crystals. So in the talk earlier, I said that when we put them together, we found that about half of them were failing. And 50% failure rate, that is rather suspicious. And what we then found was that when we were reworking the ones that failed, probably about half of those came to life as well, around a 50% failure rate. Now, what is that pointing at? This is what happens when one person designs a circuit and then someone else who doesn't understand that circuit
tries to assemble it.
Does the assembly. And if you look at the footprint that you can see there on the screen, it's polarized. That part is not a crystal, it's a crystal oscillator. And it has a ground pad and a 3.3 volt pad on opposite sides of the package. If it is 180 degrees out, guess what happens? So
and it's rectangular, so it's
it's
50%.
2 ways. So 50% failure was because I was dumping them out on the bench and putting them on essentially in a random orientation. So the 50% failure rate that we were seeing on these is 100% down to this guy. So
Statistics.
Statistics.
It works.
And the math doesn't lie.
Is that? Yeah, I think that's it from me.
Yeah. Well, I think we're just about at wrap-up time. What is it? 5:28. Technically, we finish at 5:30. So,
Did we have questions? Was there?
no, I don't think we do have questions.
I can. Oh yeah, there's a few other little notes about hardware. There are like an optional set of speakers that go to the amplifier I talked about a few times. That's just an Adafruit part number. It's in the schematic. If you get to that point, if we get to that point where things are working, that actually does make noise. I've made it make noise, just not well. John?
Yeah, and so ongoing. If you want to follow up in the short term, there is going to be the open hardware breakout room, which will keep running for the duration of the conference. So over this weekend, at least some of us will be in that room at different times so we can answer questions and things. If you have follow-up, then you can do it that way. That's probably the most immediate way of getting in touch with us. And longer term, we will have a couple of different methods for staying in touch. There is a forum running on GitHub associated with there's a discussion section on GitHub associated with the project. So we will put information about that in the breakout room chat and wherever else we can think of it. There is also the wiki. So that is at openhardwareconf.org, I think. Did I remember that correctly? Mm-hmm. Yeah. So apart from that, I would like to say thank you again to all of our speakers today, and thank you to all of you for coming along. And also, of course, the people in the room here and the dogs and cats that have supported this endeavour over the last many months, and the rest of the team. So, would any of you like to say anything?
No, just be kind to each other. It's been a pretty tough couple of years, and just hang in and support community.
Yeah. Okay. Anything, Nicola? No.
Thanks, everyone.
We'll see you in the chat. So thank you.
See you online.
And see you soon.